Picture this: a vast expanse of darkness, speckled with distant stars that shimmer like secrets waiting to be uncovered. Now, imagine standing on the edge of an unknown, staring into the cosmic abyss, where the laws of physics twist and bend in ways that defy everything we think we know. The universe is full of mysteries, and despite centuries of exploration, some of its most fundamental questions remain unanswered. Take dark energy, for example, an invisible force that's pushing galaxies apart at an accelerating rate. We know it exists, but what it is, that's a puzzle even the brightest minds can't crack, and it's just one of many cosmic enigmas that leave scientists scratching their heads. From the eerie silence of the universe known as the Fermi paradox to the bizarre behavior of black holes that warp space and time, there are phenomena out there that challenge our understanding of reality itself. Think about it. We've sent probes to the farthest reaches of our solar system, built telescopes that peer billions of years into the past, and yet the cosmos still holds onto its secrets tightly. Why do some stars suddenly vanish without a trace? What lurks in the voids between galaxies? And perhaps most haunting of all, are we truly alone in this unimaginably vast expanse? These aren't just questions for scientists, they're invitations for all of us to wonder, to explore, and to marvel at the mysteries that surround us. That's exactly what we're diving into today. We're unraveling 30 of the most mind-bending cosmic phenomena that still baffle astronomers and physicists, phenomena that remind us how much we have yet to discover. Whether it's rogue planets drifting through space without a star to call home, or the strange, unexplained radio signals from deep space known as fast radio bursts, each one of these mysteries is a piece of a puzzle we're still trying to solve. So, if you've ever looked up at the night sky and felt that tug of curiosity, that urge to understand the unknown, you're in the right place. Buckle up, because we're about to journey through the cosmos where the questions are as endless as the stars themselves. Let's start with one of the most perplexing riddles in modern astronomy: dark matter. Imagine an invisible scaffold holding the universe together, its presence felt but never seen. That's essentially what dark matter is. It makes up roughly 27% of the cosmos, yet it doesn't emit, absorb, or reflect light, making it completely invisible to telescopes. So how do we even know it exists? The answer lies in gravity. When astronomers observe galaxies spinning, they notice something strange. The outer stars move far too quickly for the visible matter alone to hold them in place. Without some unseen mass providing extra gravitational pull, these galaxies should tear themselves apart. That missing mass, it's dark matter acting like cosmic glue. But here's where things get even weirder. Despite decades of searching, no one has directly detected a single particle of dark matter. Scientists have built detectors deep underground, shielded from cosmic interference, hoping to catch a fleeting interaction. They've scanned the skies for indirect clues, like the way dark matter bends light around galaxies, a phenomenon called gravitational lensing. Yet, the more we look, the more elusive it becomes. Some theories suggest dark matter could be made of weakly interacting massive particles, or WIMP, while others propose it might be actions, hypothetical particles with bizarre quantum properties. There's even a fringe idea that dark matter doesn't exist at all, that instead our understanding of gravity is fundamentally flawed. What makes this mystery so captivating is its sheer scale. Dark matter isn't just some minor curiosity, it shapes the very structure of the universe. Without it, galaxies wouldn't have formed the way they did, and the cosmos as we know it wouldn't exist. And yet, for something so essential, it refuses to reveal itself. It's like trying to solve a jigsaw puzzle with most of the pieces hidden. Every new observation, every experiment brings us closer to an answer, or sometimes deeper into the mystery. One thing's for certain: unlocking the secrets of dark matter wouldn't just fill a gap in our knowledge, it would rewrite the story of the universe itself. If dark matter is the universe's invisible scaffolding, then dark energy is its mysterious engine pushing galaxies apart faster than gravity can pull them together. Imagine blowing up a balloon with dots on its surface. As the balloon expands, the dots move away from each other. Now, picture that expansion speeding up over time, as if some unseen hand keeps pumping more air into the balloon. That's the bizarre reality of our cosmos. Dark energy isn't just some minor curiosity. It makes up a staggering 68% of the universe's total energy, dictating its ultimate fate. But here's the kicker: we have no idea what it actually is. The story of dark energy begins with a bombshell discovery in 1998. Astronomers studying distant supernova expected to find the universe's expansion slowing down thanks to gravity's relentless pull. Instead, they saw the opposite. The universe wasn't just expanding, it was accelerating, as if some repulsive force was overpowering gravity itself. The implications were profound. Either Einstein's theory of gravity needed a major rewrite, or there was an entirely new form of energy at work. The latter won out, and dark energy was born. What makes this force so baffling is its behavior. Unlike matter or radiation, dark energy's density doesn't dilute as the universe grows. In fact, it seems to stay constant, meaning its influence grows stronger as space itself stretches. Some theories suggest it's a property of space itself, what Einstein once called the cosmological constant, a kind of background energy woven into the fabric of reality. Others propose it's a dynamic field, nicknamed quintessence, that changes over time. But here's the real head-scratcher. If dark energy keeps accelerating the universe's expansion, it could lead to a big rip, where galaxies, stars, and even atoms are torn apart in the distant future. Yet for all its dominance, dark energy leaves almost no trace. It doesn't clump like matter or interact with light. The only way we detect it is by observing its cosmic fingerprints, the way galaxies drift apart, or how light from the early universe carries faint imprints of its push. It's like trying to study the wind by watching leaves flutter without ever feeling the breeze itself. Even our most advanced telescopes and simulations can't pin it down. Some physicists wonder if dark energy hints at a deeper layer of physics, something beyond our current theories, a shadow realm of hidden dimensions or undiscovered forces. What's both thrilling and humbling is that dark energy isn't just a puzzle for astronomers. It's a frontier that straddles cosmology, quantum physics, and even philosophy. If we crack its code, we might finally understand why the universe looks the way it does, or whether it's just one of countless possibilities in a multiverse. Until then, it remains one of science's greatest blind spots, a force shaping everything we see, yet invisible to every tool we have, and that's the irony. The more we learn about the cosmos, the more we realize how much of it is written in ink we can't even see. Now, let's shift our gaze to a force so powerful it's dragging entire galaxies toward it. Meet the Great Attractor. Nestled deep within the Laniakea supercluster, a colossal web of galaxies spanning over 500 million light-years, this gravitational enigma has puzzled astronomers since its discovery in the 1970s. Here's what makes it so strange. Everything in our local cosmic neighborhood, including the Milky Way, is being pulled toward it at mind-bending speeds of hundreds of kilometers per second. But here's the catch: we can't actually see what's doing the pulling. The Great Attractor sits directly behind the Milky Way's disk, in a region astronomers call the zone of avoidance. This isn't some cosmic conspiracy, it's simply because our galaxy's dense clouds of gas, dust, and stars block our view. Imagine trying to spot a lighthouse through a thick fog, its beams swallowed by the haze. That's the challenge scientists face. Traditional optical telescopes are useless here, leaving us blind to whatever lurks in this mysterious direction. But thanks to advances in X-ray and infrared astronomy, we've begun piecing together clues. What we do know is this: the Great Attractor isn't just a single massive object, but likely a dense knot of galaxies and dark matter, a gravitational hotspot in the cosmic web. The sheer scale of its pull suggests it contains the mass of tens of thousands of Milky Ways. Yet, even that might not tell the full story. Some researchers argue there's something even larger at play, like the Shapley supercluster, lying beyond the Great Attractor, exerting its own gravitational influence. It's like discovering a river's current is actually being fed by a hidden waterfall. The real mystery, this cosmic tug-of-war, is reshaping our understanding of the universe's structure. Galaxies aren't just drifting apart due to dark energy. They're also being funneled along invisible highways of gravity toward regions like the Great Attractor. It's a reminder that even as the universe expands, the pull of hidden giants still dictates where things go. And until we find a way to peer through the Milky Way's veil, this colossal force will remain one of cosmology's most tantalizing puzzles, a reminder that sometimes the universe's biggest secrets are hiding in plain sight, just out of view. One of the most fleeting and explosive mysteries in the cosmos doesn't come from black holes or colliding galaxies. It arrives in bursts shorter than the blink of an eye. Fast radio bursts, or FRBs, are brilliant flashes of radio waves that erupt with the energy of hundreds of millions of suns, only to vanish milliseconds later. First detected in 2007, these cosmic sparks appear randomly across the sky, often billions of light-years away, leaving astronomers scrambling to catch them before they're gone. What's fascinating isn't just their power, it's how little we understand about what's causing them. Take FRB 1218, for example. This repeating burst, located in a dwarf galaxy 3 billion light-years away, pulses on a cycle so precise it could rival a Swiss watch. Then there's FRB 1900-520, which unleashed a signal so intense it distorted space-time itself, warping radio waves in a phenomenon called Faraday rotation. But here's what truly stumps scientists. Some bursts seem chaotic, like cosmic lightning strikes, while others follow eerie, repeating patterns. One leading theory points to magnetars, super-dense, highly magnetized neutron stars that sporadically release bursts of energy. In 2020, astronomers even caught one in our own galaxy emitting an FRB-like signal, offering the first direct clue. Yet not all of these bursts fit neatly into the magnetar explanation. Some exhibit structures too complex, with sub-pulses and frequency drifts that suggest something far stranger, perhaps cosmic strings, collapsing black holes, or even the remnants of ancient stellar collisions. And yes, the possibility of artificial origins, like advanced alien technology, hasn't been entirely ruled out. After all, the universe has surprised us before. The challenge: these bursts last mere milliseconds, and by the time telescopes swing toward them, they've already faded into silence. What makes FRBs more than just a cosmic curiosity is the way they interact with the universe on their journey to Earth. As these radio waves traverse galaxies, they pass through clouds of ionized gas, which subtly alters their signal. This distortion acts like a cosmic fingerprint, revealing the otherwise invisible matter between galaxies. It's as if these bursts are probes illuminating the dark highways of the universe. But to decode their full message, we'll need to catch more of them, preferably before they slip through our fingers like interstellar smoke. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars, many of which host their own planets. Given those numbers, the odds of life emerging elsewhere seem almost inevitable. And yet, when we listen, the cosmos is eerily silent. No signals, no signs of alien megastructures, no visitors knocking on our cosmic door. This glaring contradiction between probability and reality is known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "But where is everybody?" It's a question that haunts astronomers and philosophers alike, because the silence isn't just puzzling, it might be a warning. One unsettling explanation is the Great Filter Theory. Imagine an obstacle course for civilizations, with each stage more perilous than the last. The filter could be behind us, a rare fluke that let life arise on Earth but stops it nearly everywhere else. Maybe single-celled organisms are common, but intelligent life is vanishingly rare. Or worse, the filter might lie ahead. Perhaps every advanced civilization hits a wall: nuclear war, runaway artificial intelligence, ecological collapse that prevents them from reaching the stars. If that's true, our silence isn't just a mystery, it's a countdown clock. But not all theories are so grim. Some suggest aliens aren't absent, just invisible. A civilization thousands of years ahead of us might communicate in ways we can't detect, like neutrino messages or quantum entanglement. They could be observing us like we watch animals in a nature preserve, avoiding contact to prevent disruption. There's even the zoo hypothesis, which posits Earth is deliberately quarantined until we're mature enough to join the galactic community. Or consider the possibility that advanced life isn't biological at all. Superintelligent machines might have no interest in planets, preferring the cold void of space or the energy-rich centers of galaxies. Then there's the darker twist: what if we're the first? The universe is 13.8 billion years old, but complex life might need very specific conditions: stable stars, heavy elements, long periods without catastrophic events like gamma-ray bursts. We could be the pioneers, the earliest civilization to reach this point, with others following in billions of years. Or perhaps the answer is simpler. Space is mind-bendingly huge, and signals fade into noise over interstellar distances. Even if someone's out there, finding them might be like searching for a single whisper in a hurricane. The Fermi paradox isn't just about aliens, it's a mirror reflecting our own future. Every possible solution forces us to confront humanity's fragility, our potential, and our place in the cosmos. Are we alone because life is fleeting, because others are hiding, or because we haven't looked hard enough? Until we know, the stars remain a silent, haunting question mark. The night of August 15, 1977, started like any other at Ohio State University's Big Ear radio telescope, until a signal tore through the cosmic silence that would become one of astronomy's greatest enigmas. For 72 seconds, a narrowband radio burst 30 times louder than background noise, blazed from the constellation Sagittarius. It matched exactly the frequency scientists predicted an extraterrestrial signal would use: 1420 MHz, a quiet spot in the spectrum where hydrogen, the universe's most abundant element, naturally resonates. When astronomer Jerry Amon saw the data printout days later, he circled the sequence in red ink and scribbled "Wow" in the margin, a name that would stick forever. What made this signal extraordinary wasn't just its strength, but its behavior. It rose and fell in intensity like a car horn passing by, suggesting a fixed source momentarily sweeping across the telescope's field of view. That pattern ruled out earthly interference. Planes, satellites, or random noise would have behaved differently. But here's the real shocker: despite decades of searching, no one has ever detected anything like it again. Not from Sagittarius, not from anywhere. The WOW signal is a cosmic one-hit wonder, and its unresolved origins have fueled debates ever since. Some theories point to natural explanations. Could it have been a comet's hydrogen cloud briefly glowing at the right frequency? In 2017, researchers proposed two icy bodies might have been in the right place at the time, but their hydrogen signatures don't quite match the signal's unique profile. Others suggest a rogue astronomical event, like a neutron star's flare or a chance alignment of interstellar plasma acting as a cosmic magnifying glass, briefly amplifying a distant star's radio whisper. Yet none fully explain why we've never seen a repeat performance. Then there's the tantalizing possibility it was artificial. The signal's narrowband nature, like a finely tuned radio station, hints at engineered precision. If it came from a distant civilization, why hasn't it repeated? Maybe the transmitter was fleeting, like a probe or beacon that's since powered down. Or perhaps the signal was meant for someone or something else, and we just happened to eavesdrop for 72 seconds. The absence of follow-ups might even support the zoo hypothesis, where advanced civilizations deliberately avoid sustained contact. What makes the WOW signal more than just a curiosity is what it reveals about our search for cosmic company. It's a reminder that the universe can throw us curveballs, phenomena that dangle just enough clues to provoke but never enough to solve. Every new telescope, from the Allen Array to the upcoming Square Kilometre Array, scans the skies hoping for a second act. Until then, that red-inked WOW lingers as both a triumph and a taunt, proof that we might not be alone, but that the cosmos isn't ready to introduce us just yet. Imagine a star that flickers like a dying light bulb, sometimes dimming by tiny fractions, other times plunging into dramatic eclipses that blot out nearly a quarter of its light. That's exactly what astronomers witnessed with KIC 8462852, better known as Tabby's star, named after the scientist who first flagged its bizarre behavior, Tabitha Boyajian. This unassuming star in the constellation Cygnus has become one of the most perplexing cosmic puzzles of the past decade. At first glance, it resembles our own Sun, a yellow-white dwarf about 1,300 light-years away. But its light curves tell a different story. Wild, irregular dips in brightness that last days or weeks with no predictable rhythm. Stars don't behave this way, at least not naturally. The mystery began when NASA's Kepler Space Telescope, designed to hunt for planets by spotting regular dips in starlight, caught Tabby's star doing something utterly unexplainable. Planets transit in clean, repeating patterns, but this star's dimming was chaotic. Some drops were shallow, others deep enough to suggest objects 50 times wider than Earth blocking its light. Even stranger, long-term observations revealed the star's overall brightness has been fading for over a century, an unprecedented trait for a star of its type. Theories erupted like supernova. Could it be a swarm of comets, a colossal dust cloud, or, as some daringly proposed, alien megastructures, vast energy-harvesting constructs known as Dyson spheres? The Dyson sphere hypothesis, though tantalizing, faced immediate skepticism. For one, such a structure would absorb starlight and re-emit it as infrared radiation, yet Tabby's star shows no excess infrared heat. Then came the dust theory. Detailed spectral analysis revealed that the dimming events affected blue light more than red, a telltale sign of fine particles scattering shorter wavelengths. This pointed to circumstellar dust, perhaps from a shattered planet or a gargantuan asteroid collision. But even dust couldn't explain everything. The star's century-long dimming remained a head-scratcher, and the dust itself would need constant replenishment to persist over such vast timescales. What makes Tabby's star so compelling is how it exposes the gaps in our stellar knowledge. Normally, stars dim for clear reasons: sunspots, companion stars, or orbiting planets. But here, none of the usual suspects fit. Some astronomers speculate it might be consuming a nearby planet, releasing debris that periodically obscures its light. Others suggest internal stellar dynamics, like magnetic disturbances or rare vibrational modes, could be at play. The truth is, every explanation so far feels like squeezing a square peg into a round hole. This isn't just academic curiosity. Tabby's star challenges our assumptions about how stars, and by extension, cosmic systems behave. If dust is the culprit, it's dust behaving in ways we've never seen. If it's something else entirely, we might need to rewrite the textbooks. And yes, while the alien megastructure idea is a long shot, it serves a vital purpose, reminding us that the universe is under no obligation to conform to our expectations. Sometimes the most ordinary-looking star can harbor the most extraordinary secrets, and that's what keeps astronomers staring at the data, searching for the next clue in this cosmic detective story. At the heart of black holes lies a paradox so deep it threatens to unravel our understanding of reality itself. The black hole information paradox. Think about tossing a book into a fire. The pages burn, but in theory, every word could be reconstructed from the ashes and smoke if you had perfect knowledge of the physics involved. That's a core principle of quantum mechanics. Information is never truly destroyed, only scrambled. But black holes, they seem to break that rule. When matter falls into one, general relativity claims it's gone forever, crushed into a singularity where space and time cease to exist. No ashes, no smoke, just silence. This clash between quantum mechanics and Einstein's theory isn't just academic, it's a battle for the soul of physics. Enter Stephen Hawking. In 1974, he made a startling prediction. Black holes aren't entirely black, they emit radiation, now called Hawking radiation, slowly leaking energy until they evaporate entirely. Here's the catch. Hawking believed this radiation carried no information about what fell in. If true, the universe has a cosmic shredder, permanently erasing information. Quantum physicists recoiled. Losing information would mean probabilities no longer add up to 100%, breaking the very math that underpins reality. It'd be like saying 2 plus 2 could sometimes equal 5. For decades, this paradox split physicists into warring camps. Then, in 2016, a bombshell. Hawking's successors proposed that information might escape after all, encoded in subtle quantum links between particles emitted over the black hole's lifetime. Imagine a scrambled message hidden not in one letter, but in the relationships between every letter ever written. This idea, called quantum entanglement, suggests black holes might act like holograms, storing information on their surfaces while their interiors remain unknowable. Recent breakthroughs in string theory and quantum gravity hint at how this could work, with tiny quantum hairs on a black hole's event horizon preserving traces of what fell in. Yet mysteries linger. If information escapes, how does it leak slowly or burst free in a final explosion? Some theories suggest black holes might leave behind remnants, dense fossils encoding their entire history. Others argue spacetime itself might twist into knots near a singularity, creating bridges to other universes. The stakes couldn't be higher. Solving this paradox wouldn't just tell us about black holes, it could reveal the hidden language of the universe, showing how gravity and quantum mechanics finally shake hands. Until then, black holes remain the ultimate cosmic lockboxes, guarding their secrets behind event horizons where even light fears to tread. Deep in the cosmic past, long before our solar system even existed, the universe was alive with celestial beacons so bright they outshone entire galaxies, quasars. These dazzling objects, short for quasi-stellar radio sources, are actually the hyperactive hearts of young galaxies, where supermassive black holes feast on surrounding matter with such ferocity that they become the most luminous things in existence. Imagine a single object no larger than our solar system, pumping out enough energy to outshine 1 trillion suns. That's the raw power of a quasar. What makes quasars truly mind-bending is their age. The light we see from them has traveled for billions of years, meaning we're peering back into an era when the universe was just a fraction of its current age. In those chaotic early days, galaxies were gas-rich and violent, giving their central black holes an all-you-can-eat buffet. As vast clouds of dust and stars spiraled into these gravitational monsters, friction heated the material to millions of degrees, creating an accretion disk so energetic it blasted jets of plasma across space at nearly the speed of light. These jets, stretching hundreds of thousands of light-years, are like cosmic blowtorches, carving through intergalactic space and leaving behind glowing trails visible across the universe. Yet for all their brilliance, quasars hold stubborn secrets. One burning question: how did their black holes grow so massive so quickly? The most ancient quasars we've spotted host black holes weighing billions of times the sun's mass, but according to conventional physics, they shouldn't have had enough time to accumulate that much material. Did they form from the direct collapse of supermassive gas clouds in the early universe? Or were there exotic mechanisms at play, like black hole mergers on a scale we've never witnessed? Then there's the puzzle of their fuel supply. Quasars aren't eternal. They're cosmic fireworks that eventually fade when they exhaust nearby matter. But some quasars flicker on and off over surprisingly short timescales, years or even months, suggesting their accretion disks are clumpy or unstable. Others seem to switch directions, their jets wobbling like a spinning top running out of steam. These quirks hint at chaotic dynamics we're only beginning to unravel, where magnetic fields, relativistic effects, and even the black hole's spin play tug-of-war with infalling material. What makes quasars more than just distant oddities is their role in shaping the cosmos. Their intense radiation likely stunted star formation in early galaxies by blowing away gas clouds, while their jets seeded intergalactic space with heavy elements forged in their fiery cores. Some astronomers even think quasars helped reionize the young universe, stripping electrons from atoms and making space transparent to light. They're not just relics, they're the architects of the universe we see today. Yet for every answer quasars provide, they raise new questions. Why do some galaxies host quasars while others, like our Milky Way, have quiet black holes? Are quasars a universal phase all galaxies go through, or just a fluke of the early cosmos? With next-generation telescopes like the James Webb Space Telescope peering ever deeper into the past, we're closer than ever to unlocking their secrets. One thing's certain, these cosmic lighthouses still have plenty of stories left to tell. The cosmic microwave background, what we often call the CMB, is the oldest light in the universe, a faint whisper of radiation left over from the Big Bang itself. For decades, astronomers have studied its faint temperature fluctuations like a cosmic fingerprint, mapping the seeds of galaxies and testing the bedrock principle of cosmology, that the universe on large scales should look the same in every direction. But in 2005, something shook that assumption to its core. When scientists analyzed data from NASA's Oumuamua satellite, they stumbled upon an eerie pattern nicknamed the axis of evil, an alignment of CMB fluctuations that suspiciously matched the plane of our solar system. It was as if the universe's baby photo had a faint but unmistakable watermark, and it pointed directly at us. At first glance, this shouldn't be possible. The cosmological principle, a pillar of modern physics, states that the universe is homogeneous and isotropic, meaning no place or direction is special. Yet here was evidence that the CMB's fluctuations weren't entirely random. Some showed a curious preference aligning with the ecliptic, the path the sun and planets trace across the sky. The implications were staggering. Either this was a bizarre coincidence, or our solar system was somehow linked to the universe's largest-scale structures, violating one of cosmology's most sacred rules. Skeptics rushed to find flaws. Could it be an artifact of the satellite's instruments or data processing? Subsequent observations, including from the Planck satellite, seemed to confirm the anomaly wasn't just noise. The alignments persisted, though less dramatically. Some theorists proposed wild explanations, from cosmic defects left over from the Big Bang to our universe being shaped like a vast, rotating donut. Others suggested we might be seeing the ghostly influence of a neighboring universe in a multiverse scenario, its gravitational tug subtly warping our CMB. But the most unsettling possibility, that we're seeing evidence of a preferred direction in space, a cosmic north that defies everything we thought we knew. If true, it would mean the universe isn't just subtly lopsided. It might have a built-in orientation, like a giant arrow pointing somewhere we can't yet see. For now, the axis of evil remains an unsolved mystery, a crack in the foundation of cosmology. Whether it's a statistical fluke or a revolution waiting to happen, one thing's clear: the universe still has a few tricks up its sleeve, and they might just rewrite the rules we've taken for granted. When NASA's twin Pioneer probes ventured beyond the orbit of Pluto in the late 1980s, Scientists expected them to glide through the void with clockwork precision, their trajectories dictated solely by the sun's waning gravity. But something bizarre happened. Both spacecraft, billions of miles apart, began slowing down ever so slightly, as if an unseen hand was tugging them backward. This tiny but consistent deceleration, just a fraction of a nanometer per second squared, became known as the Pioneer Anomaly, a cosmic riddle that haunted physicists for decades. At first, the culprit seemed obvious: heat. The Pioneers were powered by radioactive plutonium, their interiors warm enough to emit infrared radiation. Maybe, researchers thought, this thermal glow was acting like a minuscule thruster, pushing against the probes like sunlight on a solar sail. But when they crunched the numbers, something didn't add up. The thermal radiation theory could only account for about a third of the observed slowdown. That left a gaping hole in the explanation, one big enough to fuel wild speculation. Could this be evidence of undiscovered physics, a flaw in Einstein's general relativity? Some even dared to whisper about dark matter's invisible pull or a mysterious, long-range force acting at the fringes of the solar system. The mystery deepened when newer spacecraft like Galileo and Ulysses failed to show the same anomaly. Why would the Pioneers be singled out? The answer, it turns out, was hiding in plain sight. In 2012, a painstaking analysis of decades-old telemetry data revealed the truth. The anomaly wasn't cosmic at all. It was engineering. As the probes aged, their heat distribution became lopsided, with warmth escaping unevenly from their dish-shaped antennas. This created a tiny but measurable recoil force, exactly enough to explain the deceleration. The Pioneer Anomaly wasn't a revolution in physics. It was a lesson in humility, a reminder that even the most tantalizing cosmic mysteries can have surprisingly mundane origins. Yet the story doesn't end there. The anomaly's fade into obscurity left an ironic legacy. For years, it had been a beacon for alternative theories, from modified gravity to hidden dimensions. When those explanations evaporated, so did the spotlight on deep space navigation. Today, missions like New Horizons are designed with the Pioneer Anomaly in mind, their heat budgets meticulously modeled to avoid similar surprises. What began as a glitch became a masterclass in scientific detective work, proof that sometimes the universe's greatest puzzles aren't written in the stars, but in the fine print of our own imperfect machines. In October 2017, astronomers spotted something streaking through our solar system that defied all expectations: a visitor from interstellar space. Named Oumuamua, Hawaiian for scout, this mysterious object was the first ever detected from beyond our cosmic neighborhood. Its trajectory was clear; it hadn't originated here. But what made Oumuamua truly extraordinary wasn't just its origin, it was the way it behaved. Unlike any asteroid or comet we'd seen before, this interstellar traveler didn't play by the rules. First, there was its shape. Most asteroids and comets are roughly spherical or lumpy, but Oumuamua was different. Based on its brightness variations as it tumbled through space, scientists calculated it was at least 10 times longer than it was wide, shaped like a cigar or pancake. Nothing in our solar system looks like that. Then came the real shocker. As it raced away from the sun, it sped up slightly, as if pushed by an unseen force. Comets often accelerate this way when sunlight vaporizes their ices, creating a tail. But Oumuamua showed no visible tail, no gas emissions, no dust, just that unexplained nudge. Theories exploded. Could it be a hydrogen iceberg sublimating invisibly in sunlight? Or a cosmic dust bunny, light enough for solar radiation pressure to push it? Harvard astronomer Avi Loeb proposed an even more provocative idea. Perhaps Oumuamua wasn't natural at all. Its unusual acceleration, combined with its peculiar shape, raised the faint possibility it might be artificial, a solar sail from an alien civilization drifting between the stars. While most scientists remain skeptical, the truth is, No natural explanation fits all the data perfectly. What makes Oumuamua so fascinating is the lingering uncertainty. By the time we noticed it, it was already speeding away, too distant for further study. We'll never get another look. Was it a fragment of a shattered planet ejected from another star system? A rare type of comet with invisible outgassing, or something else entirely? The universe has a habit of surprising us, and Oumuamua is a reminder that sometimes the most intriguing mysteries are the ones that slip through our fingers, leaving us with more questions than answers and a haunting sense of wonder about what else might be out there, unseen, in the vast dark between the stars. The Moon today is a quiet, barren world, lacking the churning molten core that gives Earth its protective magnetic shield. But billions of years ago, our lunar companion may have been far more dynamic, because hidden in ancient moon rocks lies evidence of a magnetic field once strong enough to rival Earth. This revelation upended everything we thought we knew about how the Moon formed. The mystery begins with samples brought back by the Apollo missions. When scientists analyzed these ancient volcanic rocks, they found something astonishing. They were magnetized as if they'd cooled in the presence of a powerful magnetic field. But here's the puzzle. For a global magnetic field to exist, a planet or moon needs a dynamo, a swirling, molten metallic core generating electrical currents through motion, like a cosmic generator. Today, the Moon's core is small, cool, and inactive. So how could it have ever produced such a strong field? One theory suggests the Moon's early dynamo was fueled by a dramatic gravitational tug of war with Earth. In its youth, the Moon orbited much closer to our planet, and the intense tidal forces may have kept its core churning violently, like stirring a cup of coffee with a spoon. Over time, as the Moon drifted farther away, this effect weakened and the dynamo sputtered out. But there's a catch. Mathematical models show this mechanism alone might not explain the strength or duration of the magnetic field recorded in those rocks. Another idea points to an extraterrestrial power source, massive asteroid impacts. Around 4 billion years ago, the Moon endured a period of violent bombardments known as the Late Heavy Bombardment. Some researchers argue these collisions didn't just scar the lunar surface, they may have superheated the Moon's mantle, creating colossal convection currents that jump-started the dynamo. Picture a pot of soup boiling over. The chaotic motion could have temporarily revived the Moon's magnetic heartbeat, yet neither explanation fully solves the riddle. The field persisted for over 1 billion years, far longer than impacts or tidal heating alone could sustain. Some scientists now speculate the Moon's core may have crystallized in a unique way, releasing latent heat and light elements that prolong the dynamo's life. Others wonder if we're missing something fundamental about planetary magnetism itself. What makes this enigma more than just a lunar curiosity is what it tells us about other worlds. If small, rocky bodies like the Moon once had magnetic fields, could Mars have held onto its protective shield longer than we thought? Might distant exomoons around gas giants harbor hidden dynamos? The Moon's magnetic past is a reminder that even the most familiar objects in our cosmic backyard still hold secrets, and sometimes the quietest places have the loudest stories to tell. If you think of the universe as a cosmic web, a vast network of galaxies strung along invisible filaments of dark matter, then the Boötes void is the web's most unsettling tier. Spanning a staggering 330 million light-years, this region of space is so empty, so unnervingly devoid of galaxies, that astronomers nicknamed it the Great Nothing. To put that in perspective, if you place the Milky Way at its center, you'd have to travel tens of millions of light-years in any direction before encountering another galaxy. It's like standing in the middle of an endless desert where even the horizon offers no respite. The discovery of this void in the 1980s sent shockwaves through cosmology. According to our best models of the universe's evolution, matter should be distributed relatively evenly, with only modest variations in density. The Boötes void isn't modest, it's a staggering anomaly, a cosmic vacuum cleaner that somehow sucked away nearly everything within its reach. Only about 60 galaxies have been found in its expanse, compared to the thousands you'd expect in a region that size. Even stranger, those few galaxies aren't randomly scattered. They're clustered into what some researchers call tendrils, as if clinging to the last threads of a crumbling scaffold. How does something like this form? One theory suggests smaller voids merged over time, like soap bubbles coalescing into one giant cavity. Another posits that dark energy, the same mysterious force accelerating the universe's expansion, might have stretched this region to extremes, pushing galaxies outward until only silence remained. But here's the problem. Simulations of cosmic evolution struggle to produce voids this large. If our models can't explain the Boötes void, does that mean we're missing a fundamental piece of the puzzle? Yet the void isn't just a cosmic curiosity, it's a mirror reflecting our own limitations. When astronomers first mapped it, they assumed it was truly empty. But deeper observations revealed faint dwarf galaxies hidden in the shadows, suggesting even nothingness might be more complex than we thought. It's a humbling reminder that the universe doesn't conform to tidy categories. What we call emptiness might just be a different kind of order, one we don't yet understand. The Boötes void forces us to confront an uncomfortable truth. The universe might be lumpier, messier, and far stranger than our theories predict. And if patches this empty exist, what else might be lurking in the darkness, waiting to append everything we think we know? The cosmic microwave background is often described as the universe's baby picture, a near-perfect snapshot of the infant cosmos frozen in time. But there's a strange blemish in that picture, a chilling anomaly lurking in the constellation Eridanus. Known as the cold spot, this region of the CMB is noticeably colder than its surroundings, as if someone took a cosmic ice cube and pressed it against the fabric of space-time. At first glance, it might seem like a minor statistical quirk, but the scale of this cold patch is anything but ordinary. Stretching over 1.8 billion light-years, it's one of the largest structures ever identified, and its existence defies easy explanation. The leading theory points to the Eridanus supervoid, a vast, sparsely populated region of space that might overlap with the cold spot. Voids aren't uncommon. The universe is full of bubble-like gaps where galaxies are scarce. But this one is different. If the supervoid is real, it would be among the largest ever discovered, so enormous that light passing through it should lose energy as it fights against the void's weaker gravitational pull, a phenomenon called the integrated Sachs-Wolf effect. This energy loss could theoretically cool the CMB light we observe, creating the cold spot. The math checks out except for one problem. When astronomers searched for the Eridanus supervoid, they found hints of underdense regions, but nothing large or empty enough to fully account for the temperature drop. It's like trying to explain a deep freeze with just a crack in the window. That missing piece has fueled wilder ideas, including the possibility that the cold spot isn't a void at all, but the fingerprint of a collision with another universe. In the multiverse scenario, our cosmos might be one bubble in an endless froth of universes, each with its own physics. If one of those bubbles brushed against ours in the distant past, the energy released could have left a scar, a cold imprint on the CMB. It's a radical idea, but not entirely implausible. The cold spot's temperature patterns bear an uncanny resemblance to what such a collision might look like a bruise from a cosmic bump. Yet skeptics push back. Could this just be a statistical fluke, a random fluctuation magnified by our human tendency to find patterns? The CMB is a tapestry of hot and cold spots, most of which fit neatly within the expected noise of the early universe. The cold spot stretches those limits. It's a 3 sigma anomaly, meaning there's only a 0.26% chance it's random. Unlikely, but not impossible. And without definitive proof of the supervoid's size or a smoking gun from alternative theories, the debate rages on. What makes this cosmic whodunit so compelling is what it reveals about our place in the universe. If the cold spot is just a void, it's a reminder of how little we understand about the large-scale structure of the cosmos. If it's evidence of a multiverse, it rewrites the story of reality itself. Either way, this enigmatic patch of sky challenges us to ask, are we staring at a cosmic defect, a measurement error, or a window into something far larger than we ever imagined? The answer, much like the cold spot itself, remains just out of reach, a tantalizing mystery written in the faintest whispers of the universe's oldest light. We've mapped galaxies, peered into black holes, and even detected the faint echo of the Big Bang, but here's something bizarre. About half the ordinary matter in the universe has gone missing. Not dark matter, not some exotic particle, but the stuff we're made of: protons, neutrons, electrons. Scientists call this the missing baryon problem, and it's one of cosmology's most glaring blind spots. According to our best calculations, the universe should contain far more visible matter than we've actually found. So where is it all hiding? The answer might lie in a cosmic hide-and-seek game taking place in the vast spaces between galaxies. For decades, astronomers suspected this missing matter could be tied up in what's called the warm-hot intergalactic medium, or WIM, a ghostly web of superheated gas, too diffused to glow like stars but too energetic to stay invisible forever. Picture steam rising from a boiling pot, except this steam is 1,000,000 degrees hot and stretches millions of light years between galaxies. Detecting it isn't easy. This gas doesn't emit much light, but occasionally it absorbs certain wavelengths as distant quasars shine through it, leaving faint fingerprints in their light. In recent years, advanced X-ray telescopes like Chandra and XMM Newton have begun spotting these whispers. They've found evidence of oxygen atoms in the WIM, stripped of electrons and glowing at extreme temperatures. Even more telling, observations of the cosmic microwave background suggest this intergalactic fog could account for a significant chunk of the missing matter. But here's the catch: the numbers still don't quite add up. While we've found some of the WIM, there's likely more lurking in even harder to detect forms, perhaps as ultra-diffuse filaments or as gas so hot it's nearly transparent. Then there's the possibility that some baryons are hiding in plain sight, just in forms we didn't expect. Could they be tied up in rogue planets floating freely between stars? Or in vast, undetectable clouds of cold molecular gas? Some researchers have even speculated about primordial black holes, formed in the chaos of the early universe, swallowing matter without a trace. The challenge is that every time we think we've closed the gap, the universe throws us another curveball, like a magician with an endless supply of tricks. What makes this more than just an accounting error is what it reveals about the universe's structure. If half the ordinary matter is truly hiding in these hard-to-see places, it means the cosmic web is far more intricate and far more dynamic than we ever imagined. The missing baryon problem isn't just about finding lost atoms, it's about rewriting the map of the universe one invisible thread at a time. And until we solve it, we're left with a humbling thought: even the stuff we think we know is still out there waiting to be found. Picture this: two of science's most trusted tools, each meticulously cross-checked, each operated by brilliant minds, yet they keep giving us different answers to one of cosmology's most fundamental questions: how fast is the universe expanding? This isn't just a minor disagreement, it's a full-blown crisis called the Hubble tension, and it's shaking the foundations of modern astronomy. On one side, we have measurements of the early universe, like the cosmic microwave background, suggesting an expansion rate of about 67 kilometers per second per megaparsec. On the other, observations of nearby stars and supernova consistently land closer to 73. That gap might seem small, but in the precise world of cosmology, it's a canyon. And the scariest part, the more we refine our measurements, the wider the gap grows. This isn't just about numbers, it's about our understanding of reality itself. The Hubble constant isn't some abstract figure. It's the universe's speedometer telling us how quickly space itself is stretching. If our measurements don't agree, it implies something's missing from our cosmic playbook. Maybe dark energy isn't as constant as we thought. Perhaps there's an unknown particle zipping through the cosmos, tweaking gravity at grand scales. Or, in the most radical scenario, our bedrock theory of the Big Bang Lambda CDM might need a rewrite. The stakes couldn't be higher. If the tension persists, we're not just tweaking a formula, we're peering into the unknown, staring at the possibility that the universe has secrets we haven't even begun to guess. What makes this debate so electrifying is how it splits the scientific community. Some argue the discrepancy is just systematic error, flaws in how we measure distant supernova or interpret the cosmic microwave background's faint whispers. Others think it's a sign of new physics, a cosmic curveball waiting to be uncovered. There's even a third camp suggesting the early and late universe might simply behave differently, as if the laws of physics evolved over time. Imagine if gravity itself wasn't constant but changed subtly over billions of years. It sounds like science fiction, but when the data refuses to align, even the wildest ideas get a seat at the table. For now, astronomers are throwing everything they've got at the problem. New telescopes like the James Webb Space Telescope are scrutinizing distant stars with unprecedented precision, while next-generation observatories like the Vera Rubin Telescope will map millions of galaxies hunting for clues. Every observation, every simulation is a piece of the puzzle, and that's the beauty of the Hubble tension. It's not just a problem to solve, but a reminder that the universe is still full of surprises. Whether it leads us to a tweak in our models or a revolution in physics, one thing's certain: the cosmos isn't done teaching us yet. At the heart of our galaxy, something strange is glowing, not in the visible light our eyes can see, but in high-energy gamma rays that paint the Milky Way's core with an eerie, unexplained light. This mysterious emission, known as the galactic center excess, has puzzled astronomers since it was first spotted by NASA's Fermi Gamma-Ray Space Telescope in 2009. The glow forms a diffuse halo around the supermassive black hole Sagittarius, a star, stretching thousands of light-years across. And here's what makes it so baffling. None of the usual suspects, neutron stars, supernova remnants, or cosmic rays colliding with gas, can fully account for its intensity or peculiar shape. The most tantalizing explanation: dark matter. Theorists suggest that if dark matter particles collide and annihilate each other, they could produce gamma rays as a byproduct. The Milky Way's core, with its dense concentration of dark matter, would be the perfect place for this to happen. Some models even predict that weakly interacting massive particles, or WIMP, could create an emission pattern eerily similar to what Fermi observed. It's a compelling idea, one that could finally give us a direct glimpse into the invisible scaffolding of the cosmos. But not everyone's convinced. Critics point to a hidden population of pulsars, rapidly spinning neutron stars that beam out gamma rays like cosmic lighthouses. These objects are faint individually, but clustered together in the galactic center, their combined glow might mimic the excess. Supporting this, astronomers have detected similar gamma-ray signals in other dense stellar environments, like the Andromeda Galaxy, where pulsars are abundant. Yet even this theory has holes. The galactic center excess is smoother than expected for a collection of point sources, and the energy spectrum doesn't quite match known pulsar emissions. It's like hearing a chorus where every voice is slightly out of tune, close but not quite right. The debate takes another twist when you consider millisecond pulsars, old neutron stars revved up by stealing material from companion stars. These could explain both the excess's smoothness and its energy profile. But here's the catch: we'd need an implausibly large number of them, far more than current models predict. It's as if the galaxy's core is hiding a pulsar factory no one told us about. What makes this mystery so captivating isn't just the science, it's the stakes. If the excess is dark matter, it's a once-in-a-generation breakthrough. If it's pulsars, it challenges our understanding of stellar evolution, and if it's neither, then something entirely new is waiting to be discovered. For now, the galactic center excess remains a cosmic Rorschach test. Every scientist sees a different possibility in its glow, and the truth might be stranger than any of them imagine. Saturn's North Pole holds a secret that defies everything we know about planetary weather, a colossal, six-sided hurricane so precise it looks like it was drawn with a cosmic ruler. This is the Saturn hexagon, a geometric storm spanning nearly 20,000 miles wide, large enough to swallow 4 Earths side by side. Unlike the chaotic swirls and spirals we see in other gas giants, this hexagonal jet stream has maintained its razor-sharp edges for decades, possibly even centuries. How does a storm this massive, this perfect, exist in nature, and why haven't we found anything like it anywhere else in the solar system? The hexagon was first glimpsed by the Voyager probes in the 1980s, but it wasn't until Cassini arrived in 2004 that we got a clear look. High-resolution images revealed a towering wall of clouds, with winds screaming at over 300 miles per hour, yet despite that fury, the structure itself remains eerily stable. Think of it like a spinning top. No matter how fast it goes, the shape holds. That stability is the real puzzle. On Earth, storms dissipate as they clash with land or cooler ocean waters. But Saturn is all gas with no solid surface to disrupt the flow. So what's keeping this six-sided beast in check? One leading theory points to laboratory experiments with spinning fluids. When scientists rotate a liquid rapidly in a circular tank, waves can form at the edges, sometimes taking on polygonal shapes, including hexagons. On Saturn, the planet's own rotation might be sculpting the jet stream into this geometric pattern, like a cosmic version of those fluid dynamics tests. But here's the catch: those lab-made shapes are fleeting, flickering in and out of existence in seconds. Saturn's hexagon has outlasted generations of scientists. What gives it such staying power? Another clue lies in the storm's depth. Cassini's instruments revealed the hexagon isn't just a surface feature. It plunges hundreds of miles into Saturn's atmosphere, a towering structure of layered winds and circulating gases. Some researchers think this vertical stability might act like an anchor, preventing the hexagon from unraveling. There's also the curious role of smaller storms that orbit inside the hexagon's boundaries like captive moons. These vortices might help reinforce the main structure, their gravitational nudges keeping the larger pattern intact. Yet for all these theories, no one can fully explain why this phenomenon only appears at Saturn's North Pole. The South Pole, by contrast, hosts a more conventional circular storm. Some speculate the hexagon requires a very specific recipe, a precise balance of wind speed, planetary rotation, and atmospheric depth that only Saturn's northern hemisphere provides. Others wonder if it's a temporary feature, a fluke of current conditions that could vanish over geologic time. The hexagon isn't just a scientific curiosity, it's a masterclass in how much we have yet to learn about planetary atmospheres. If we can crack its code, we might unlock secrets about fluid dynamics that apply far beyond Saturn, from Earth's own jet streams to the raging storms on distant exoplanets. For now, it remains one of the solar system's most mesmerizing mysteries, a storm that refuses to play by the rules, a swirling, six-sided enigma etched into the clouds of a gas giant. And every time we think we're close to understanding it, the universe reminds us that some of its most breathtaking wonders are also its most stubborn puzzles. Beyond the orbit of Neptune, in the icy outskirts of our solar system, lies a cosmic traffic jam. The Kuiper Belt, a sprawling ring of frozen leftovers from the solar system's formation. Here, dwarf planets like Pluto and Eris mingle with countless smaller objects, all dancing in the distant chill of the sun's fading light. But something strange happens when you reach about 50 astronomical units out, roughly 7.5 billion kilometers from the Sun. The belt doesn't taper off gradually as you'd expect. Instead, it slams into an invisible wall with a number of objects plummeting so sharply, astronomers call it the Kuiper Cliff. It's as if someone drew a line in the cosmic sand and said, "No further." This sudden drop-off isn't just curious, it's a full-blown anomaly. The Kuiper belt should theoretically extend much farther, with icy bodies becoming sparser the farther you go. But the cliff suggests something disrupted this orderly distribution, and scientists have two leading suspects. The first is a hidden planet, a so-called Planet 9, lurking in the darkness beyond the belt, its gravity shepherding objects inward and clearing a path. Computer simulations show a massive world, perhaps 5 to 10 times Earth's mass, could explain the sharp edge by tugging objects into clustered orbits or flinging them into the abyss. But so far, no telescope has spotted this elusive giant, leaving the theory tantalizing but unproven. The other possibility is even more dramatic, a violent rearrangement of the solar system in its infancy. According to the NICE model, a leading theory of planetary migration, the giant planets Jupiter, Saturn, Uranus, and Neptune didn't form where they are today. Instead, they shifted positions billions of years ago, with Neptune likely plowing outward into the Kuiper belt. This upheaval could have scattered countless objects, leaving behind the stark boundary we see now. Yet even this explanation has gaps. Some objects beyond the cliff, like the distant dwarf planet Sedna, have orbits that don't quite fit the model, hinting at additional forces at play. What makes the Kuiper Cliff more than just a celestial curiosity is what it reveals about our cosmic backyard. If Planet 9 is real, its discovery would rewrite our solar system's map and challenge our understanding of planetary formation. If it's a relic of ancient chaos, it's a frozen snapshot of a time when the planets themselves were still restless, carving their paths through the debris of a younger, wilder solar system. Until we send probes beyond this invisible barrier or catch a glimpse of the unseen forces shaping it, the Kuiper Cliff remains a silent sentinel, a reminder that even in our own cosmic neighborhood, the universe still holds its secrets close. When the universe was just minutes old, a cosmic alchemy forged the first simple elements: hydrogen, helium, and a dash of lithium. This process, called Big Bang nucleosynthesis, should have left behind a measurable amount of lithium-7, an isotope we can calculate with startling precision. But here's the catch: when astronomers measure lithium levels in the oldest stars' relics from the early cosmos, they find only a third of what the math predicts. This glaring mismatch, known as the lithium problem, isn't just a tiny discrepancy. It's a gaping hole in our understanding of how the universe's first atoms formed and evolved. One place to look for clues is inside stars themselves. Ancient stars, like those in the Milky Way's halo, act as cosmic time capsules. Their atmospheres preserve chemical compositions unchanged for billions of years, offering a snapshot of the early universe. Yet these stars show lithium levels far below what Big Bang models forecast. If the lithium didn't vanish, where did it go? Some theories suggest these stars destroy lithium over time. Imagine a celestial blender's stellar interiors churn so violently that lithium atoms, fragile compared to heavier elements, get torn apart in nuclear reactions. But here's the problem: even accounting for this destruction, the numbers still don't add up. Stars shouldn't be that efficient at obliterating lithium. Then there's the wildcard possibility: new physics. Could our Big Bang models be missing something fundamental? Some theorists propose exotic solutions, like undiscovered particles interacting with lithium in the early universe, or variations in the strength of fundamental forces during nucleosynthesis. Others wonder if lithium is hiding in plain sight, locked away in unseen reservoirs like cosmic dust or diffuse gas clouds. But none of these ideas fully bridge the gap between prediction and observation. The lithium problem isn't just about one element, it's a crack in the foundation of cosmology. If we can't trust our predictions for lithium, what else might we be getting wrong? Every telescope pointed at ancient stars, every simulation of the early universe, inches us closer to an answer. Until then, this missing lithium serves as a humbling reminder. Even our best theories are still works in progress, and the universe keeps a few cards close to its chest. Black holes come in two familiar flavors, small ones born from dying stars, and supermassive giants lurking at the centers of galaxies. But tucked between these extremes lies a cosmic unicorn, the elusive intermediate mass black hole, a missing link in our understanding of how these gravitational monsters grow. In 2021, astronomers may have finally caught one of these rare beasts, nicknamed the unicorn, for its uniqueness and location in the constellation Monoceros. At just 3 times the mass of our Sun, this tiny titan defies expectations. It's not a stellar black hole, yet far too small to be supermassive. So how does something like this even exist, and why are they so hard to find? The unicorn wasn't spotted directly. No black hole ever is. Instead, researchers noticed a red giant star behaving oddly, its light rhythmically stretching and compressing as if tugged by an unseen companion. Calculations revealed an invisible object with enough gravity to warp its partner but emit no light of its own, a black hole but shockingly lightweight. Most stellar black holes form from collapsed stars at least 20 times the Sun's mass, leaving behind remnants 5 to 15 times heavier than our Sun. The unicorn, at just 3 solar masses, sits right on the edge of what physics says is possible. Could it be the remnant of a failed supernova, a star that collapsed without the usual fireworks? Or perhaps a primordial black hole forged in the chaos of the early universe? This discovery hints at a hidden population of black holes we've barely begun to explore. Intermediate mass black holes ranging from hundreds to hundreds of thousands of solar masses are the holy grail of cosmology. They could solve the mystery of how supermassive black holes grew so quickly after the Big Bang. Imagine a cosmic stepping stone, smaller black holes merging over time, building mass like snowballs rolling downhill. Yet until now, evidence for these middleweights has been scarce. A few candidates, like the object HLX-1 in a distant galaxy, glow brightly enough to suggest intermediate mass, but most remain ghosts in the data. The unicorn offers a new way to hunt them by watching for their gravitational influence on nearby stars. What makes these black holes so elusive is their stealthy nature. Unlike supermassive black holes that light up by devouring gas and stars, or stellar black holes in binary systems that emit X-rays as they siphon material from a companion, intermediate mass black holes often lurk in isolation, with nothing nearby to reveal their presence. They're the introverts of the cosmos, dark, quiet, and easily overlooked. But if the unicorn is any indication, they might be more common than we thought, hiding in plain sight, waiting to rewrite the story of how black holes shape the universe. Every new discovery peels back another layer, proving that even in the darkest corners of space, surprises are always lurking. On clear, moonless nights just after sunset or before dawn, if you're far from city lights, you might spot a faint, ghostly glow stretching upward from the horizon, a triangular wash of light sometimes mistaken for twilight. This is the zodiacal light, sunlight reflecting off countless dust particles scattered across the inner solar system. For centuries, it was considered a beautiful but straightforward phenomenon, until astronomers realized there's something deeply wrong with the dust creating it. According to our best models, the amount of dust needed to produce the zodiacal light's glow should come primarily from asteroid collisions and comet debris. But here's the paradox: when we tally up all the known sources, the grinding of asteroids, the icy crumbs left by comets, we're left with only about 10% of the dust required to explain the light's intensity. It's as if someone left a lamp on in an empty room, and no matter how hard we search, we can't find the bulb. one possibility is that we're underestimating Jupiter's role as a cosmic vacuum cleaner. The gas giant's immense gravity might be funneling dust inward from the outer solar system, creating a hidden reservoir we haven't accounted for. Another theory points to interstellar dust, tiny particles drifting in from beyond our solar system, caught in the sun's gravitational web. But even these explanations fall short, leaving a glaring gap between prediction and observation. The most intriguing twist comes from recent spacecraft data. NASA Juno mission, while studying Jupiter, accidentally measured dust impacts far exceeding expectations. These high-velocity particles weren't just drifting lazily, they were racing through space, suggesting a dynamic, fast-moving dust population we've barely begun to map. Could this be the missing source, or is there some completely overlooked process like electrostatic forces or solar wind interactions, lifting and concentrating dust in ways our models don't yet capture? What makes this more than just a cosmic accounting error is what it reveals about our solar system's hidden mechanics. The zodiacal light isn't just a celestial curiosity, it's a flashlight illuminating the invisible dance of dust, gravity, and sunlight. Every unanswered question forces us to reconsider what we think we know about the space between planets, reminding us that even in our own cosmic backyard, mysteries lurk in the most unexpected places. And until we solve this paradox, that eerie glow will remain both a guide and a riddle, pointing toward secrets we're only beginning to uncover. High above the sulfuric acid clouds of Venus, where the atmosphere churns with pressures that could crush a submarine, one of the solar system's most hypnotic storms rages endlessly. At the planet's south pole, two colossal whirlwinds spin in perfect harmony, forming a double-eyed vortex unlike anything seen on Earth. This isn't just a temporary hurricane, it's a permanent, self-sustaining maelstrom, a freak of atmospheric physics that's baffled scientists since its discovery in 2006. What makes this vortex so bizarre is its structure. Instead of a single spinning eye like Earth's hurricanes, Venus's polar storm splits into two distinct centers, connected by a snaking funnel of clouds that resembles a cosmic infinity symbol. The entire system rotates once every 2 to 3 Earth days, powered by super-rotating winds that scream across the planet at speeds up to 220 miles per hour, 60 times faster than Venus itself spins. It's as if the atmosphere has a mind of its own, divorcing entirely from the rocky surface below. The leading theory suggests this duality arises from something called a polar dipole, a pair of swirling low-pressure zones forced together by Venus's peculiar atmospheric dynamics. On Earth, hurricanes dissipate when they hit land or cool waters, but Venus has no oceans or continents to break the cycle. Its thick, carbon dioxide-rich atmosphere acts like a global fluid, with rising hot air at the equator and sinking cold air at the poles, creating a relentless conveyor belt of energy. This constant churning might stabilize the double vortex, locking it in place like a celestial gyroscope. Yet even this explanation feels incomplete. Why two eyes instead of one? Why don't they merge or drift apart? The European Space Agency's Venus Express orbiter gave us our closest look, revealing storm clouds that plunge over 20 miles into the vortex's depths, dragging sulfur compounds into a spiraling dance. But here's the twist: while the overall structure persists, the details shift constantly. Clouds morph, winds fluctuate, and temperatures vary wildly between the vortex's edges and core, a chaos that defies simple models. Some researchers speculate that atmospheric waves, similar to Earth's jet streams but far more violent, might sculpt the vortex's shape. Others wonder if Venus's extreme greenhouse effect, with surface temperatures hot enough to melt lead, fuels turbulence we don't yet understand. The deeper mystery is why Venus alone hosts such a spectacle. Mars has polar caps but no vortices. Jupiter's great red spot is a solitary storm. Even Saturn's hexagon pales in comparison to this binary tempest. Is it Venus's slow rotation one day that lasts longer than its year? that allows the atmosphere to dominate, or does its lack of a magnetic field let solar wind interact with the atmosphere in unique ways? Every probe sent to Venus raises new questions, proving that behind its shroud of clouds, the planet guards its secrets fiercely. What makes the Venus vortex more than just a planetary oddity is what it teaches us about fluid dynamics everywhere. From Jupiter's bands to Earth's ocean currents, the same physics governs fluids across the universe. Crack Venus's code, and we might unlock universal truths about how energy flows in swirling systems, whether in a gas giant storms or a cup of stirred coffee. Until then, this double-eyed sentinel keeps spinning, a mesmerizing reminder that even our closest planetary neighbor still holds mysteries no terrestrial storm could ever rival. Mars has teased us with a gas that shouldn't be there, methane, a simple molecule that keeps appearing and vanishing in the planet's thin atmosphere like a cosmic will-o'-the-wisp. On Earth, methane is often a calling card of life, produced by everything from burping cows to microbes deep underground. But on Mars, its sporadic presence has become one of the most tantalizing and frustrating enigmas in planetary science. The detections come and go without warning, sometimes spiking to 10 times background levels before disappearing within weeks. So where is it coming from? And why can't we pin it down? The first whiff of Martian methane came in 2004, when Europe's Mars Express orbiter caught traces of the gas at just 10 parts per billion. That might sound negligible, but methane shouldn't last long in Mars' atmosphere. Ultraviolet radiation from the sun breaks it apart within a few hundred years. Its presence implies an active, ongoing source. Then came the curveballs. NASA Curiosity rover, sniffing the air in Gale Crater since 2012, has recorded unpredictable methane surges, some as high as 21 parts per billion. Even stranger, Europe's Trace gas orbiter, equipped with superior methane-detecting instruments, has repeatedly failed to confirm these spikes from orbit. It's as if the gas appears only in isolated pockets, vanishing before most instruments can get a second look. The leading theories split into two camps: geology or biology. Underground, methane could form when water reacts with olivine-rich rocks in a process called serpentinization, something we see in Earth's hydrothermal vents. Mars might also harbor hidden reservoirs of ancient methane, trapped in icy cages called clathrates, occasionally leaking through cracks, but the biological possibility is what quickens pulses. On Earth, 95% of methane is biologically produced. Could Martian microbes buried deep where liquid water might still linger be exhaling this gas? The idea isn't far-fetched. Earth's extremophiles thrive in similar conditions, sealed away from surface radiation. Adding to the intrigue, some data suggests methane levels follow seasonal cycles, peaking in northern summer. Is the sun's warmth thawing shallow subsurface ice, releasing trapped gas? Or could dust storms play a role, their winds stirring up buried reservoirs? The problem is, every explanation has a flaw. Geological processes should produce steadier emissions, not erratic bursts. And if life is the culprit, why haven't we found other organic molecules to back it up? The mystery deepens when you consider transportation. Methane doesn't just appear, it has to travel. On Mars, where winds are fierce and the atmosphere thin, gas should disperse rapidly. Yet Curiosity's spikes suggest plumes so localized, they're almost like invisible geysers erupting right beneath the rover. Some scientists speculate unseen fractures or porous rock layers might channel methane in concentrated jets, explaining why orbiters miss the brief ground-level surges. What makes this detective story so gripping is the stakes. If the source is geological, it could point to active hydrothermal systems, places where life might cling today. If it's biological, it would be the most profound discovery in human history. But until we catch the culprit red-handed, Mars methane remains the ultimate planetary whodunit. A puzzle written in a gas we can barely measure, flickering in and out of view like a cosmic Morse code we're still learning to read. Early in the morning of June 30th, 1908, a blinding fireball tore across the skies of Siberia, a silent streak of light that ended in an explosion so powerful it flattened 800 square miles of remote forest, snapping trees like toothpicks in a perfect radial pattern. This was the Tunguska event, a detonation with the force of 10 to 15 megatons of TNT, roughly 1,000 times more powerful than the atomic bomb dropped on Hiroshima. But what made this cosmic impact unlike any other was what it didn't leave behind. No crater, no fragments, no smoking gun. Just an eerie silence where a wilderness once stood, and a mystery that's puzzled scientists for over a century. At first glance, the culprit seems obvious, a meteor or comet exploding in Earth's atmosphere. But the devil's in the details. Most airbursts, like the Chelyabinsk meteor in 2013, scatter debris across the impact zone. Tunguska yielded nothing. Expeditions to the site in the 1920s and 30s found trees charred and stripped of branches, yet no traces of extraterrestrial material. Even the soil showed no chemical fingerprints of a cosmic visitor. It's as if the universe threw a punch, then vanished without leaving a single fingerprint. The leading theory points to a stony meteoroid, roughly 60 meters wide, that disintegrated 5 to 10 kilometers above the ground. The heat and pressure of atmospheric entry would have vaporized it instantly, releasing a shockwave that rippled outward like a nuclear blast. But here's the twist. Computer simulations struggle to replicate the sheer scale of destruction without any surviving fragments. Some researchers argue it might have been a fragile comet, made mostly of ice and dust, which would explain the lack of debris. Yet comets typically leave telltale gases in the upper atmosphere, and no such evidence was recorded in 1908. Then there are the wilder possibilities. Could it have been a chunk of antimatter annihilating itself in a flash of energy, or a microscopic black hole passing through Earth leaving no trace except devastation? These ideas, while thrilling, lack credible evidence. More plausible but equally unsettling is the notion that Tunguska was a rare meteorite made of porous, loosely packed material, something so brittle it turned to dust mid-explosion, like a sandcastle hit by a wave. What makes Tunguska more than just a historical curiosity is what it teaches us about planetary defense. If a similar object struck a populated area today, the casualties would be catastrophic. Yet despite advances in astronomy, we still can't predict or fully explain events like this. The Tunguska event lingers as a humbling reminder that the universe keeps throwing curveballs, and sometimes the most destructive ones leave the least evidence behind. It's a cosmic detective story with no final answer, just a century of dead trees and unanswered questions whispering from the Siberian taiga. The universe is supposed to have rules, laws that dictate how stars are born, live, and die. But HD 140283, nicknamed the Methuselah star, laughs in the face of those rules. This ancient flicker of light drifting through the constellation Libra carries an impossible secret. Based on our best measurements, it might be older than the universe itself. Discovered over a century ago, this unassuming yellow subgiant didn't raise eyebrows until astronomers calculated its age. By analyzing its composition, especially its shockingly low metal content, they realized this star was a relic from the cosmic dawn, a time when the universe was still cooking its first heavy elements. The numbers came back staggering: 14.5 billion years old, give or take 800 million. There's just one problem. The universe itself is only 13.8 billion years old. That's like finding a fossilized bone older than the Earth. It shouldn't exist. So how did we get this so wrong? The answer lies in the star's unique fingerprint. HD 140283 is a population 2 star, part of an ancient generation that formed before heavier elements like iron were common. Its atmosphere is nearly pristine, almost entirely hydrogen and helium, making it a time capsule from an era before planets, or even most stars, existed. But pinning down its exact age is fiendishly tricky. Imagine trying to guess a person's birthday by the wrinkles on their face, except the person might predate time itself. Astronomers use two main clocks to date stars: radioactive decay and stellar evolution models. For Methuselah, the latter suggested an age that broke cosmology. But here's the twist: recent updates to our understanding of stellar physics have chipped away at that number. By accounting for the star's unusual oxygen-rich composition and refining measurements of its distance thanks to the Hubble Space Telescope, the age estimate dropped to around 14 billion years. Still older than the universe, but now within the margin of error. Others argue the star could be as young as 12 billion years, which would solve the paradox, but that requires ignoring some of its most primordial traits. The real lesson here isn't just about one star, it's about the gaps in our cosmic ledger. If HD 140283 truly predates the universe, it means our models of the Big Bang are incomplete, perhaps missing hidden dimensions, exotic physics, or even cycles of cosmic rebirth. More likely, it's revealing flaws in how we measure stellar ages. Stars don't come with birth certificates, and the farther back we look, the fuzzier the numbers get. What makes Methuselah so captivating is its defiance. It's a reminder that the universe, for all its apparent order, still holds puzzles that refuse to fit neatly into our equations. Every time we think we've nailed down the timeline of existence, a flicker of light from the void whispers, "You're missing something," and that's the beauty of astronomy. The stars we study aren't just objects. They're mirrors reflecting back how much we have yet to learn. In 1954, newspapers buzzed with a startling claim: the U.S. Air Force had detected an unknown satellite orbiting Earth, predating humanity's first official launch of Sputnik by 3 years. Dubbed the Black Knight, this mysterious object became the stuff of legend, sparking theories that ranged from alien surveillance to remnants of an ancient advanced civilization. But how much of this story holds up under scrutiny, and why does this orbital enigma still captivate imaginations decades later? The tale gained traction when amateur radio operators reported picking up strange signals in the 1920s, followed by military radar blips in the 50s that seemed to track an unidentified object. Conspiracy theorists latched onto grainy photos, some later debunked as space debris or thermal blankets lost during shuttle missions, as proof of a 10,000-year-old alien satellite silently watching us. The lore deepened with claims that Nikola Tesla intercepted its signals, or that it appeared in medieval tapestries. Yet beneath the myth lies a kernel of intrigue. Earth's orbit is littered with unexplained debris, some behaving in ways that defy easy classification. Scientists offer more mundane explanations. The signals were likely natural radio noise or early satellite experiments kept classified during the Cold War. Modern tracking catalogs over 20,000 pieces of orbital debris, from dead satellites to discarded rocket stages, some tumbling in ways that create erratic radar returns. One prime candidate for Black Knight sightings, a piece of the Discoverer 5 satellite launched in 1959, whose reflective surface could mimic an artificial object's glow. Even the famous anomalous photos from the 1990s were later identified as a lost thermal blanket from the STS-88 mission. But here's what keeps the mystery alive: not all orbital oddities have been neatly explained. In 2018, a cigar-shaped object named Oumuamua zipped through our solar system, reigniting debates about artificial versus natural space visitors. Meanwhile, the U.S. government's recent UFO disclosures have fueled speculation that some debris might not be of earthly origin. The truth likely lies somewhere between conspiracy and cosmic coincidence, a reminder that even in an age of advanced astronomy, the skies above us still hold pockets of mystery. Whether the Black Knight was ever real matters less than what it represents. Our endless fascination with the idea that we might not be alone and that the universe's secrets could be closer than we think. The idea sounds like pure science fiction, a rocket engine that pushes forward without expelling any fuel, like a car driving endlessly without gas. Yet for over 2 decades, the EmDrive has dangled this tantalizing possibility, promising to rewrite the rules of propulsion while baffling physicists in equal measure. The concept is deceptively simple: a hollow, cone-shaped chamber pumped full of microwaves. According to its inventors, the chaotic bouncing of these microwaves generates just enough net thrust to nudge the device forward, seemingly defying Newton's third law, the bedrock principle that every action must have an equal and opposite reaction. Early laboratory tests only deepened the mystery. In 2016, NASA EagleWorks team reported detecting minuscule but consistent thrust from their EmDrive prototype, a whisper of force that shouldn't exist under known physics. Peer-reviewed journals cautiously published the results, sparking both excitement and skepticism. If real, the implications would be revolutionary: spacecraft gliding between planets without fuel, missions to Mars cut from months to weeks. But here's the catch: no one could explain how it worked. The thrust measurements were achingly small, teetering on the edge of experimental error, and theories to explain them veered into speculative territory. Some invoked quantum vacuum fluctuations, while others suggested hidden interactions with dark energy. Critics pounced. The thrust, they argued, could easily be experimental noise, thermal expansion of the device, magnetic interference, or even the subtle push of air currents in the lab. When the German Aerospace Center tried replicating the experiment in 2018, their EmDrive produced no thrust outside the margin of error. Yet other teams, like China's Northwestern Polytechnical University, claimed success, muddying the waters further. The debate reached a fever pitch when a group at Dresden University proposed a mundane culprit: heat. Their simulations showed thermal effects could mimic the thrust signature, tricking instruments into seeing motion where none existed. What makes the EmDrive more than just a laboratory oddity is what it reveals about the scientific process itself. Extraordinary claims demand extraordinary proof, and here the proof remains frustratingly elusive. Even negative results serve a purpose. They sharpen questions, expose flaws, and force inventors to refine their designs. The EmDrive's legacy might not be a working engine, but a lesson in humility. For now, it lingers in limbo, not quite debunked, not quite confirmed, a ghost of possibility hovering at the edge of known physics. Whether it's a glitch or a gateway, one thing's certain: the universe still has a few surprises left, and the EmDrive is a reminder that sometimes the most controversial ideas are the ones worth chasing. Deep in the cosmic microwave background, that ancient afterglow of the Big Bang, lies a cold spot so vast and unexplained it sparked one of the most heated debates in modern cosmology. Stretching nearly 2 billion light-years across the constellation Eridanus, this frigid anomaly is about 70 microkelvin colder than its surroundings, a tiny difference on paper, but statistically so unlikely it hints at something profound. The simplest explanation points to the Eridanus supervoid, an enormous, sparsely populated region of space where the absence of galaxies might stretch and cool light passing through it, like a marathon runner losing steam climbing a hill. But here's the catch: when astronomers mapped this supposed void, they found it far too small and shallow to account for the cold spot's dramatic chill. It's like blaming a single ice cube for freezing an entire lake. The math just doesn't add up. This discrepancy has led to a far wilder possibility: that the cold spot isn't a void at all, but the bruise from a collision with another universe. In the multiverse theory, our cosmos could be one bubble in an endless froth of universes, each with its own physics. If one of these bubbles grazed ours in the distant past, the energy released might have left an imprint on the CMB, a cosmic fingerprint visible today as this inexplicably cold patch. The idea isn't as far-fetched as it sounds. Simulations show such a collision could create patterns eerily similar to the cold spot, like ripples from a pebble dropped into the fabric of space-time. Yet skeptics argue it's a stretch, a cosmic Rorschach test where we're seeing connections that might not exist. After all, the CMB is a tapestry of hot and cold fluctuations. Statistically, a few anomalies are bound to arise purely by chance. What makes this debate so electrifying is what's at stake. If the cold spot is just a void, it forces us to rethink how structure forms on the largest scales, exposing gaps in our understanding of cosmic evolution. If it's evidence of a multiverse, it shatters the notion that our universe is alone, opening doors to realities beyond our wildest imagination. For now, the cold spot remains suspended between these two worlds, a tantalizing enigma that refuses to be neatly explained. Every new observation, from next-generation telescopes to refined void mapping techniques, peels back another layer of the mystery, reminding us that even the universe's oldest light still holds secrets we've only begun to decipher. From dark energies accelerating push to the fleeting whispers of fast radio bursts, the cosmos is brimming with mysteries that defy our understanding. We've explored 30 of the most baffling enigmas, black holes that vanish information, galaxies pulled toward unseen giants, and stars that flicker as if something artificial obscures their light. Each one challenges the limits of our knowledge, proving the universe is far stranger than we ever imagined. What makes these puzzles so thrilling isn't just their complexity, it's how they ignite curiosity. The WOW signal, the Saturn hexagon, Oumuamua's odd acceleration, they remind us that discovery isn't about having all the answers, but about asking the right questions. Every anomaly is a thread in a grander tapestry, pulling us closer to truths we can't yet grasp. And while some mysteries may one day yield to science, others might linger for centuries, keeping that spark of wonder alive. So here's the real takeaway. The universe isn't a static museum exhibit. It's a dynamic, evolving riddle, and you're part of the story. The next time you look up at the night sky, remember somewhere out there, a star is vanishing without a trace, a planet might harbor hidden oceans, and forces we can't yet name are sculpting the cosmos. Stay curious, stay questioning, and who knows, the next great cosmic revelation could be just one observation away. If these mysteries captivated you as much as they've fascinated scientists, hit that like button, share your thoughts in the comments, and subscribe to join us as we unravel the next wave of cosmic enigmas. The universe has spent billions of years writing its secrets. Let's decode them together.